Huawei is very dangerous.
Rarely does a country go to war with a private company.
We have met the enemy, and it is Huawei.
We're not going to do business with Huawei.
Huawei represents a national security risk.
But is this really about Huawei, or is it something bigger than that?
A headline drops that makes Silicon Valley freeze. China announces a 1 nanometer chip. Not a roadmap, not a prototype, but a working chip. If you believe the hype, they've achieved what TSMC and Samsung won't reach until 2027 or later. But here's what nobody's telling you. The reality is far more complicated than the headlines suggest. In April 2025, researchers at Fudan University, led by professors Jiaorong and Bao Zhang, published findings in the journal Nature about a chip called Wuji. This 32-bit RISC-V microprocessor uses 2D materials like molybdenum disulfide instead of traditional silicon. The chip contains 5,900 transistors and has a thickness of less than 1 nanometer. That's the truth behind the sensational claims. But let's be clear about what this actually means. This is a research prototype. It's not mass production. It's not powering smartphones or data centers. The previous record for 2D semiconductor circuits was just 115 transistors in a 2017 chip from Vienna University of Technology. So, yes, Fudan's achievement is impressive, a 51 times improvement in transistor count, but it's laboratory science, not industrial revolution. The same team also developed POX, a flash memory device that writes data in 400 picoseconds, roughly 25 billion operations per second. That's genuinely groundbreaking speed. They achieved a 94.3% yield rate on their hybrid 2D silicon chip. These are real accomplishments, but they're happening in controlled academic environments, not billion-dollar fabrication plants churning out millions of chips monthly. Now, let's talk about what's actually happening in commercial chip manufacturing. TSMC began mass production of 2 nanometer chips in the second half of 2025, with yields reportedly above 60%. They're using gate-all-around transistor technology for the first time. Apple, Nvidia, AMD, and other major customers have already locked in capacity. Samsung also started 2 nanometer production in late 2025, but they're struggling. Reports indicate their yields are around 40% compared to TSMC's 60%. Their 3 nanometer yields are stuck at 50%, while TSMC achieves 90%. That 40-point difference in yield translates to billions in wasted silicon and higher costs. The current industry leader TSMC won't reach 1.4 nanometer until 2028 or later, and true 1 nanometer production isn't expected until 2030. According to their roadmap, these require high-NA EUV lithography machines from ASML. Each machine costs over $150 million and contains 100,000 parts. Only ASML makes them. China cannot buy them. Here's where the ITRS standards come in. They say a 1 nanometer node should have a contacted gate pitch of 42 nanometers and a tightest metal pitch of 16 nanometers. So 1 nanometer isn't even literally 1 nanometer. It's marketing nomenclature for a generation of chip technology. Fudan's work proves 2D materials can function at extreme scales. It shows Chinese researchers are pushing boundaries in material science. But there's a canyon-sized gap between a 5,900 transistor research chip and the billions of transistors in modern processors. Here's where China's actual progress gets interesting. SMIC, China's leading foundry, shocked the world in September 2023 when Huawei released the Mate 60 Pro smartphone powered by the Kirin 9000S chip. Tech Insights confirmed this was a 7 nanometer chip made by SMIC using older DUV, deep ultraviolet lithography, not EUV. That shouldn't be possible according to conventional wisdom. But SMIC used multi-patterning techniques, printing the same pattern multiple times to achieve smaller features. It requires 34 lithography steps compared to just 9 steps with EUV. The result? SMIC's 7 nanometer costs 40 to 50% more than TSMC's equivalent, and yields are below 50%. For 5 nanometer, which SMAC is reportedly developing, yields could drop to 30 to 40%. That's economically catastrophic for commercial production. But China doesn't care about profit margins. The government subsidizes these operations through the National Integrated Circuit Industry Investment Fund, known as the Big Fund. In March 2023, they injected $1.9 billion into Yangtze Memory Technologies. SMEC's capital expenditure reached $7.47 billion in 2023, a 17.6% increase from 2022. This isn't business. By 2025, Chinese foundries are expected to account for over 25% of global capacity among the top 10 mature node foundries. China's monthly wafer production capacity hits 7.6 million pieces, representing 25.6% of global semiconductor capacity. They're expanding aggressively at 28 nanometer and 22 nanometer nodes, disrupting global pricing and squeezing competitors like UMC in Taiwan and global foundries in the US. Then, in November 2025, Huawei launched the Mate 7 Air with a starting price of 4,199 yuan, equivalent to approximately $580. The device measures an impossibly thin 6.66 cm, earning it the distinction of being the thinnest flagship in the entire Mate series history. What's even more remarkable is that Huawei managed to pack a massive 6,500 mAh silicon carbon battery into this ultra-slim profile. The frame utilizes aerospace-grade titanium alloy, the same material choice that mirrors Apple's recent iPhone Pro models, but at literally half the cost. The display is a massive 7 inches, providing users with expansive visual real estate that exceeds the iPhone 16 Pro Max's 6.9-inch display and the Samsung Galaxy S24 Ultra's 6.8-inch screen. The app situation tells another remarkable story. When Google Play became unavailable, pessimists predicted users would abandon Huawei phones in droves. Instead, Huawei's app gallery now serves 580 million monthly active users. Major developers are racing to ensure their apps work perfectly on Harmony OS, with over 50 AI-powered applications already integrated into the system. Meanwhile, SMIC continues grinding forward. They're making 7 nanometer chips work without EUV, albeit expensively and inefficiently. They're pushing toward 5 nanometer. Reports suggest they've achieved it using self-aligned quadruple patterning, though commercial products haven't appeared yet. Every chip SMIC produces under sanctions is a statement. Not that they've caught up, but that they won't stop trying. The US responded by tightening restrictions. In November 2024, TSMC stopped shipping 7 nanometer and below chips to Chinese AI companies. The Netherlands partially revoked ASML's export licenses for DUV machines to China. In December 2024, US prosecutors revealed Operation Gatekeeper, uncovering a smuggling network that moved $160 million worth of NVIDIA H100 and H200 GPUs to China between October 2024 and May 2025. The tech war escalates daily. But the real bombshell came in March 2025. Photos surfaced from inside a Huawei facility in Dongguan showing something that should not exist. China appears to have built a working EUV machine using a completely different technology called laser-induced discharge plasma. Trial production is scheduled for the third quarter of 2025, with mass manufacturing targeted for 2026. ASML's monopoly exists because EUV lithography is outrageously difficult. The machines use light with a wavelength of 13.5 nanometers to etch circuits onto silicon wafers. That is 5,000 times smaller than a human hair. To generate this light, ASML fires a 30 kilowatt laser at microscopic tin droplets flying through a vacuum chamber at 50,000 times per second. When the laser hits the tin, it creates plasma hot enough to emit EUV radiation. The entire process requires over 100,000 parts from 800 global suppliers, including Zeiss lasers from the United States and Zeiss optics from Germany. ASML spent over 20 years and billions developing this technology, and they are the only company that has successfully commercialized it. But China responded with the largest technological mobilization in history. Between 2022 and 2024, Beijing funneled over $75 billion into domestic semiconductor development through state banks and sovereign wealth funds. More than 50,000 engineers were reassigned from companies like Huawei and CMEEIIC to classified research facilities. Satellite imagery revealed dozens of new chip fabrication plants rising across Shanghai, Shenzhen, and other cities. The breakthrough came from an unexpected direction. While ASML uses laser-produced plasma technology requiring massive lasers and complex control systems, Chinese researchers at Harbin Institute of Technology developed an alternative called laser-induced discharge plasma. Instead of directly hitting tin droplets with high-power lasers, the LIDP approach vaporizes tin between electrodes, then converts it to plasma through high-voltage electrical discharge. The result is the same 13.5 nanometer wavelength EUV radiation, but achieved through a simpler, smaller, and potentially cheaper system that reportedly consumes 40% less power than ASML's approach. Photos posted on social media by industry sources in March 2025 showed optical interferometers and assembly equipment at Huawei's Dongguan facility. Chinese text on the machinery identified it as an EUV lithography objective lens assembly from the Chongqing Institute of Optics. Multiple sources confirmed that trial production is scheduled for the third quarter of 2025, with mass manufacturing targeted for 2026. The technical challenges remain enormous. Current LIDP prototypes produce between 50 and 100 watts of EUV power, but commercial lithography requires at least 250 watts for viable manufacturing throughput. ASML's latest machines produce over 500 watts. The Chinese system also faces bottlenecks in multi-layer mirrors, photomasks, and photoresists, all areas where Western suppliers maintain significant leads. But here's what Western analysts keep missing. China does not need to build a better machine than ASML. They just need one that works well enough for domestic needs. China represents 30% of global semiconductor demand and has a massive captive market. Military and strategic applications do not require cutting-edge yield. Even a 70% effective Chinese EUV machine would be revolutionary for Chinese chipmakers currently stuck using expensive multi-patterning workarounds. ASML stock dropped 7% in March when news of China's EUV testing emerged. The company made 42% of its third quarter 2025 sales to China, primarily older DUV machines. ASML plans to build 20 high-NA EUV machines per year by 2028 at $380 million each, targeting customers like Intel, TSMC, and Samsung. If China develops its own alternative, that calculus changes dramatically. The global semiconductor industry is splitting into two parallel ecosystems. The Western Alliance continues with ASML machines at TSMC foundries making chips designed by NVIDIA, Apple, and AMD. Meanwhile, China is building an entirely separate system with domestic EUV machines at SMIC foundries producing chips designed by Huawei and Cambricon. For AI development, this matters enormously. Every advanced AI model from ChatGPT to Claude runs on NVIDIA chips made with ASML machines. If China gains independent EUV capability, Chinese AI companies like DeepSeek, Baidu, and Alibaba will no longer face chip access bottlenecks. The United States loses its primary leverage over Chinese technological advancement, and AI development becomes truly global. Western analysts predicted China would need a decade to reach 7 nanometer production, yet Huawei shipped 7 nanometer chips in the Mate 60 Pro by 2023. China consistently exceeds Western expectations by finding alternative paths to the same goals. ASML's monopoly lasted 20 years because nobody else tried this hard. Now someone is trying, backed by unlimited resources and national determination. So, what's the verdict on the 1 nanometer claim? It's real in a laboratory sense. Fudan University built functioning devices at atomic scale using 2D materials. But calling this a 1 nanometer chip in the same category as TSMC's roadmap is misleading. These are different technologies, different architectures, different purposes. The race continues, and the gap, while narrowing, remains measured in years, not nanometers. The outcome will reshape not just the semiconductor industry, but the global balance of technological power for decades to come. Are we witnessing the end of Western semiconductor dominance? Drop your thoughts in the comments below, and if you found this breakdown valuable, hit that subscribe button because this story is far from over.